Chapter 15 is on thermodynamics. So that's the study of processes in which energy is transferred as heat and as work. So we want to look at some of these results. We want to remember that heat's the transfer of energy due to a temperature difference, and work is a transfer of energy independent of the temperature. So in these kinds of systems, we talk about the system and the environment. So the system is whatever you're studying. Maybe it's my ice cube and my glass of water. So it's the ice cube and the water and perhaps the glass, but not the air in the room or the table it's sitting on. So the system would be the ice cube, the water, and the glass. The environment is everything else. And we try in physics when we're doing calculations, especially in taking data, to isolate the system from the environment. So a closed system is one in which no mass leaves or enters, but energy may be exchanged with the environment. An open system, mass and energy may enter and leave. So we want to isolate our systems to get the best results. We've already talked about the zeroth law of thermodynamics, that if two objects touch and they're in thermal equilibrium, they'll have the same temperature. The first law of thermodynamics says that energy is always conserved. This is sometimes called the law of conservation of energy. And you can write it just as a mathematical equation. You could write out that delta U is equal to Q minus W, where delta U is the heat content, W is the work done, and delta U is the change in internal energy. But I'm more of a fan of energy is always conserved. You have heard me talk before about conservation problems. We did conservation of momentum especially. So anything where you can conserve energy makes the math more direct. With these kinds of problems, you would want to watch out for the negative signs, for the positives and negatives, because they can sneak in and confuse you. So positive work means work is done by the system on the surroundings. Negative work means work is done on the system by the surroundings. Positive Q means heat's added to the system. Negative Q means heat leaves the system. So if you've got an isolated system and heat's not allowed to enter or leave, the work done will equal to the change in heat energy will equal 0, and the change in internal energy is going to be also 0. So let's look at work in a confined gas. So work done on a confined gas, work is force times distance. But for our gases, that's going to be P times delta V, where P is the pressure and delta V is the change in volume. Pressure is force over area, if you'll remember. And anyhow, we can make the math work out. But for us, the work is pressure times change in volume. So what's really cool about this is we can draw a PV diagram, a pressure volume diagram. So if you draw a pressure volume diagram, pressure is usually on the vertical axis, volume is usually on the horizontal. And we start out at initial volume and initial pressure, and we end up at final volume and final pressure. And you'll notice I have two graphs, one on the left, one on the right. They both should start out at the same initial conditions and end at the same final conditions. But they have a different path to achieve that end. You'll notice that in the one on the left, it's a direct path, and on the one on the right, I keep the pressure constant for a while, and then it spikes up. So what we want to notice is that if we said work is pressure times change in volume, on these kinds of graphs, work is going to equal the area under the curve. Work is equal to the area under the curve. If you don't think you're going to remember that, you might want to underline it in your notes. Work is equal to the area under the curve. So it's really easy to compare two systems and see which one requires the most work by looking at these PV diagrams. everybody ought to be able to tell that the area under this straight line and the area under this curved line are different. And in fact, the straight line has the biggest area and the curved line has the smaller area. So more work on the left, less work on the right. Work done depends on our path, so it is a result of a non-conservative force. If you carry out your process at a constant temperature, we say it's isothermal. If we restrict it so heat is not allowed to flow into or out of the system, we call it adiabatic. We're just learning some terms. If you need this for your specific discipline, they'll define these terms for your specific instances. And I'm trying not to add too many physics terms to clutter up your brain. The heat engines and the second law of thermodynamics. So heat flows naturally from a hot object to a cold one. That is a statement of the second law of thermodynamics. So we've had the zeroth law. At the start of this chapter, we had the first law, and now we've got the second law. Heat flows naturally from hot to cold. Any machine that turns heat energy into mechanical work is a heat engine. So an internal combustion engine, an engine that runs off burning gasoline, is a heat engine. Your electric car, if you've got one that works strictly off a battery or that you plug it in, is not a heat engine. So in a heat engine, the general schematic would have some sort of a heat source. So for my car, that's the burning gasoline. It would produce energy that would input into the engine. The engine would do some sort of work. And then there would be waste heat, leftover heat that didn't get converted 100% into work. That waste heat goes into something we call the heat sink. S-I-N-K. A heat sink is a receptacle for waste heat energy. Notice that the heat source and the heat sink are at different temperatures. The heat source is at a high temperature, T2. The heat sink is at a much lower temperature, T1. We need those differences in temperature to have heat energy flow from the heat source into the engine and then out to the heat sink. If you didn't have them at different temperatures, your heat engine would overheat because there'd be no way to remove the extra heat energy, and heat source and the engine would achieve the same temperature, and that would be very bad. So the engine works when heat flows from hot to cold, so T2 has to be greater than T1. The energy in is equal to the work out plus your waste heat energy, and it's never going to be 100% efficient. There's always some waste heat, there's always some lost energy. And our percent efficiency is going to be the work out divided by the energy in, and then times 100%. So the greater we can have our temperature difference between our heat source and our heat sink, the more efficient your engine. In your automobile, the radiator is your heat sink. And when your car is not functioning properly, your radiator is going to overheat. Carnot cycle. In physics, we talk about the Carnot cycle. So this is an ideal reversible cycle trying to show you how heat energy would flow through a theoretical engine. So it's not for real things, it's for idealized engines. Because in the real world, there are no reversible processes. Energy is always lost somewhere along the line, and you can't just throw it in reverse. All natural processes are irreversible. What the Carnot cycle will do is describe the most efficient heat engine possible, and it gives us upper limits for heat engine efficiencies. So typically the diagram has 4 parts to it. You'd go from A to B on a curve, B to C on a curve, C to D, and D back up to A. So it goes round and round and round. Going from A to B, we'd add heat energy, QH, so heat energy is being added. From C to D, heat energy is being removed. And B to C and D to A, there are changes in our volume. There's an expansion B to C and a compression D to A. The top line, A to B, takes place at a constant high temperature. It's an isotherm. The bottom line, D to C, takes place at a constant colder temperature. So that's a different isotherm, T sub C. The little graph on the right is supposed to show you your heat source. The circle is the heat engine, and the blue box is the heat sink. So energy goes in, work comes out, waste energy goes to the heat sink. Sometimes when you're talking about these, it helps to think of things in terms of a cylinder with a piston, and there's compression and expansion and intake and exhaust. But we are not going to overdo that. If you can tell me that a Carnot cycles for an idealized heat engine and that it sets upper limits for heat engine efficiencies, it has 2 isotherms and 2 adiabats, and the shape is kind of like a swished box, I would be happy. Entropy. Entropy is a measure of the disorder of a system. We could restate the second law of thermodynamics as natural processes tend toward a state of greater disorder. If you have an ice cube, all your H2O molecules are organized in their rigid little places. Then when you begin to melt it, they sort of go a little crazy and haywire, and they're just everywhere. So the ice cube has an entropy, but the puddle of water has more entropy. And if we turn that puddle of water into steam, we would have even more entropy, even more disorder. Some examples they tend to give in books are ink and water. If you have a drop of ink and water, the minute you drop it in, that's as organized as it's going to get. Ink separate from water. Over time, the ink is going to swirl through the water, and molecules will move around, and disorder will increase. Old age, I know you're not worried about that yet, but as you get older and older, your hearing deteriorates, your sight deteriorates, your sense of smell goes haywire. All these things sort of fall apart as you get older and older and older. So have a little sympathy for your grandparents. Housework. Oh, I've always thought entropy was a reason why I hated housework, especially dusting. You dust, and the same day it will come back. Disorder. Entropy is a quantitative measure of the disorder of the system. That means you can come up with a numeric value. Entropy is measured in delta S, that's the symbol for it. The units are joules per degree Kelvin, joules per degree Kelvin, and delta S is equal to Q divided by T, Q divided by T. So the entropy of your isolated system is never going to decrease. It always increases. It can't stay constant, but not for very long. And for that reason, because it never gets smaller, it always increases over time. Sometimes in books they refer to entropy as times arrow, because if you can plot increasing entropy, that's the direction time is increasing in. And another thing that we talk about associated with entropy is heat death. Heat death is the time when the universe will achieve a maximum state of disorder and all objects will have the same temperature. So the universe is at thermal equilibrium when we are at heat death. Everything has the same temperature, everything has maximum disorder. And that is all we are going to say on the subject. Again, this is just a little assortment of terms, something to get you thinking about it.